class, this video is on topic D5, interference patterns in thin films. And this concept of thin film interference explains the beautiful rainbow surface that you see in this photo of a soap bubble wand. And maybe even the timing of this lesson is appropriate given that June is Pride Month. Here are some examples of iridescence, which is an optical phenomenon where surface appears to change color when you change the angle of the view. And thin film interference is one of the reasons why these beautiful surfaces exist for many examples of plants, animals, and specifically, it is the reason why non-living things like soap bubbles and camera lenses look this way. Recall that the visible spectrum of light is from 380 nanometers to 740 nanometers, and white light is composed of all these wavelengths within this range. And recall also why an object would appear to have a color. So when a camera lens looks blue, it's because most of the light that enters your eye has the wavelength of blue light. White light can be separated into its components through refraction, which we've seen before in this unit, dispersion, which we have talked about in this unit, and constructive and destructive interference patterns. So we've never been seeing colors from constructive and destructive interference until today. So for thin films, when we say that in science, we mean a layer of very thin material which causes constructive and destructive interference patterns between various lengths. The thin film is usually on a supporting material, for example, if it's coating, and the thin film is usually, that refers to either somewhere between a fraction of a nanometer to a few nanometers thick. So remember, nanometer is times 10 to the minus 9. Take this this schematic for an example. If this was a zoomed in version of a soap bubble, you have air and then the film and then air. And reflection or transmission can happen at this top boundary and the bottom boundary. And although all the colors will have this reflection, only a specific wavelength based on the thickness of the film will reflect in a way that the crests will line up and will have constructive interference between the light that reflects at the top boundary and the light that reflects on the bottom boundary. So this light reflected and this light reflected may have constructive interference, and the wavelength of that light, that color corresponding to that wavelength, will be more visible. Constructive interference for sound means that you'll hear something louder. For light, it means brighter. So there will be a light that will be most intense when there is a special in-phase condition that occurs for that wavelength. And if there was an even coating, you would be seeing the one color or narrow color range. But if the thickness changes, then you see a rainbow. And that is because the thickness of the film determines the color of the light that will be strongly reflected in a way that results in constructive interference, or the waves, the two reflected waves being in phase. The thicker the film, the longer the wavelength. So if you see oil on water, so let's say oil has dropped onto the asphalt from a car, leaking from a car, and then it rains and oil floats on the water. You can see this little puddle of oil is thinner in some spots than others, and there is a rainbow pattern because there is varying thicknesses of the oil. There are really great video resources with animation, so I'm putting those, I'm highly recommending that you do watch those short animations to really help solidify this. So let's get into the details. So light that hits a boundary is both reflected and transmitted in a very particular way based on the indices of refraction of the boundary materials. So the way that there is reflection and transmission depends on comparing the indices of refraction, not reflection. So here is light hitting a boundary, and you have some light that bounces back and some light that goes through. Notice the transmitted waves are never inverted. So if you have a crest going in, it ends up being a crest on the other side, regardless of how optically dense the second medium is. But so transmission, there's never inversion. We're going through, the refracted part is never inverted. However, the reflected part, when it bounces back, it may be inverted. You might consider this to be a phase change of 180 degrees, or you might call this an inversion, but it's the same thing. The textbook calls them phase changes of 180 degrees. I'm just gonna say inverted because I think it's a bit easier. So when you're going into a faster medium, there is no inversion. When you're going into a slower medium, there is inversion. And what do we mean by like faster or slower medium? The medium is more optically dense if it has a higher index of refraction. So the lower the n value, the faster light travels through it. So here we have a higher index to a lower index. N1 is bigger than N2. Of course, there's no inversion on transmission, so the crest, it becomes a crest going through it. But the reflected wave, we question whether there's an inversion. In this case, where we're going to a faster medium, there is no inversion. So the crest going to the right is still a crest going to the left. But when n is smaller than n2, so we're going to a slower medium, the transmission is not inverted, but the reflected wave is inverted. So you could also think of this as a phase change of 180 degrees. The crest to the right becomes a trough to the left. So if we break down the steps for this example, we have light in air, white light in air, or actually let's pick a specific wavelength of light in air that travels towards this air-oil boundary. And then that thin layer of oil is sitting on glass. Light traveling from air meets the top surface of a thin oil layer, so right here. And some light waves are reflected and inverted. So we have the reflected waves, the reflected portion here. Then light rays in the oil layer, the part that gets transmitted or refracted, it travels down to the bottom, and then there's a second reflection possible. So the first reflection possible was here, and if it didn't reflect there, it might reflect here. So it may or may not be inverted depending on the refractive index of what's below it. In this case, since glass is more optically dense, it has a higher index of refraction than oil. It is a slower medium, and there is going to be an inversion. So there's an inversion here, there's an inversion here. These two reflected rays, the one that was reflected earlier and the one that was reflected later, may interfere constructively or destructively, depending on the phase difference. If this phase difference, or the path difference from here to here, this is this extra path that the second wave had to travel along, it's equal to 2t. And if 2t is a specific value compared to the wavelength, then we'll get full constructive interference. If 2t is a specific distance based on the wavelength, it will be a destructive interference. And the thickness of the film is either something we're going to solve for or something we're given. So reflected light, those two reflected light rays, they will interfere constructively or destructively based on the indices of refraction of the different materials at the boundary, causing reflection and maybe inversion, and then the thickness of the film. So we need to be able to compare n values, unless we're solving for that, and we need to be able to observe the thickness of the film, and 2t is the path difference. Or maybe we're solving for that and we know everything else. So this slide, there's nothing new, that we know that when two waves are in phase, we get constructive interference. This is when crests line up with crests. And out of phase is when there's destructive interference, when crests line up with troughs. And I'm just reminding you of this because our first example is going to ask if there is constructive interference of these two reflected waves or destructive interference or something maybe in between. So let's just blow up example 1A. We have an incident wave light ray, and there is some reflection and some transmission, and then there is reflection at the second boundary. And we want to know, is this reflected wave and this reflected wave fully in phase or fully out of phase or something in between? The thickness of the film, actually, sorry, let's go here first. Let's compare the optical densities. So we've got air and then film. The film is more optically dense. Light is slower in the film. So there is going to be inversion here. And then from film to air, air is less optically dense. So it's the faster medium. So there's not going to be inversion here. So let's draw a diagram and take a closer look. And in order to draw the diagram, I'm going to sort of extend the two light rays, the two possibilities horizontally. So I'm going to look at one path of reflecting early and inverting. So we have N2 bigger than N1. We draw a wave, and then we're going to invert it. So when a wave is inverted, we've drawn a trough, and we're just about to draw a crest. But because that would be natural, but because it's inverted, we're going to do what's unnatural and make it a trough again. So this is representing this path. There's another option for the light. If it doesn't get reflected at the beginning, it could go through the depth of the film. So it could go T all the way there, and then it is reflected, and then T distance back, and then it emerges, and it may or may not have an interference with the blue. I've just used color to try and explain and sort of color code my diagrams, connecting my diagrams, but this is not like necessarily red light, and certainly the red light doesn't turn into blue light. I'm just color coding here. So we've got the shorter path is this. And we've got inversion right here. The longer path, let's take a look at how much longer is the longer path. So the light goes into the film and then comes out of the film. Each time it does one of those trips, it's pi over 4. So 2t would be pi over 2. So we're going to draw the longer path, which is this red. And then the first dotted line represents going from air to film, and there's no inversion there because it's just transmission and there's never inversion. And then we're going to travel 2t more, and N3 is not bigger than N2. So air is a faster medium, and there's not going to be inversion. So here, after we do that crest, we're going to continue to do the natural thing and not invert it. We're going to do a trough. And then this is the outside air after reflection, the blue, and this is the outside air after reflection, the green. And notice that they are perfectly in phase, which means that's constructive interference. And there's different ways for that constructive interference could occur. The constructive interference would have worked out if it was a half wavelength, 3/2 wavelengths, 5/2 wavelengths. Anytime it was a half wavelength increment, it would have worked out. In this particular scenario where we have one inversion at one reflection, but not the other reflection. I guess one more thing to mention here is that when sometimes the thickness is expressed as a ratio of a wavelength, this is the wavelength as it is inside the film. When I say transmission or reflection, but really it's refraction or reflection because the light that makes it into the film will have a different wavelength according to the universal wavelength equation. So that's maybe just a fine detail to note because of the derivation of an equation we're going to use later. But this is the wavelength as the light is traveling through the film. So it has to be in that form. Okay, so when we only had one inversion, the film could be any half wavelength increment of wavelength, and we would get constructive interference. And that was when we had fast to slow to fast media. So example 1b, now we have air to film to glass, but it's otherwise the same problem. The thickness is lambda over 4, which means the 2t, the extra path length, the longer path length is lambda over 4 times longer. So I've drawn out my two options for path. So here's the shorter path. The shorter path goes from here, reflects here, and it is inverted because film is a slower medium. So we invert there, and then this time the longer path. So we have the boundary between air and film, and the transmission or the refraction here, it doesn't cause inversion, like it never does. And it's a half a wavelength. And then, because glass is even slower, light through glass is even slower than light through a film, there's going to be inversion. And now you can see what's coming out of the air, the reflected wave, in the two reflected waves, they are perfectly out of phase, which means there's destructive interference. And this would have, again, the destructive interference would have happened with the two reflections for any half wavelength increment of, any 1/2 increment of wavelength. So here it was going fast to slow to even slower, and we had two inversions. If we had the film was 0 lambda, 1 lambda, 2 lambda, or 3 lambda out of phase, then we could have done constructive. So these are just two examples where you are trying to visualize whether the two reflected rays are in phase or out of phase. And it really depends on how many inversions you have and the thickness of the film. So we've seen this slide before. In phase means constructive, out of phase means destructive. And we had to really look at the diagram and see if crest lines up with crest or crest lines up with trough, the green and the blue. But there's a little bit more detail. Now we realize we can't just come up with a rule for path difference or for the film thickness to determine constructive or destructive, because we also have to consider how many inversions at the reflection. So if one of the two inversions, so only one of the two inversions was, only one of the two reflections was an inversion, then these path difference options gives you constructive interference. And if only one of the reflections was inversion, then these give you destructive, and it's the opposite if you have two inversions. So I wrote all of this out because it is important for the derivation of the equations we're going to use, but I have to be honest, I don't memorize this. I don't memorize this. I just draw out a diagram and I figure it out from there. And the equations are given to you. The formula, it is open book formula. So you don't have to memorize this, but it is important to understand why there's this flipping. So some problems involve calculating the thickness of a film. And we still don't actually have an equation that relates wavelength and thickness. So let's go a bit further. So light waves that reflect from the two surfaces of a thin film produce interference that depends on the path length traveled by the two waves, which is the film thickness, maybe times 2. And then the wavelength of the light, which is lambda. Any phase changes that occur from the reflection, the indices of refraction for the material involved. So there's got to be an equation that can be derived that connects T with lambda with N. And so here are the equations for when we have one of those reflections causing an inversion. The textbook says phase change, but phase change by 180 degrees is just an inversion. So I'm just going to say inversion because I find it's easier. So if we go from air to film to air, there's going to be inversion here, but not here. And these are the equations. 2t equals n plus a half lambda divided by n of the film, the index of refraction of the film. And this is the equation for constructive interference. So if you want to know what wavelength is going to be constructively interfered based on a certain thickness. Or you could do it the other way around. If you're given that it's red light and you're given the wavelength, and you'd have to be given the index of refraction, you could pop in a few different M values to get what are the possible thicknesses of the film that would let that red light be constructive interference. So hopefully this is obvious now when the thickness is changing, like that puddle of oil, why you can get a rainbow, because if the thickness is changing, then along like across the puddle, you'll get different light colors that are constructively interfering. Yeah, T is the thickness of the film in meters. Wavelength is lambda in meters. Index of refraction of the film, you would have to be given the substance. You'd have to be given what that film is made up of, or you'd be given the number directly. And of course, there are tables to look up the indices of refraction. So if both waves have inversions or phase changes, notice how they are the exact same two equations, but they are flipped. There's constructive because of the whole number ratios of lambda, whereas there is half multiples of the wavelength for destructive when you have two inversions. Anyways, just make sure that you're using the right equation. I'll do one example to show you how you might set this up. So in example 2, a thin film of glycerin is on the surface of water as shown below. If red light, and that has a wavelength of 633 nanometers, is shone onto the surface of the thin film, what minimum thickness will provide constructive interference? So this is, we want red light to be the one that has constructive interference. What is the T that will work for that? What are the, there are multiple values of T that will work for red. So what is the minimum? So let's blow up this, this diagram. So we have two reflections, one right here, the shorter path length. There is going to be inversion because glycerin has a higher index of refraction. And then going from glycerin to water at this boundary, there's no inversion because this is a faster medium. So we're going to pull up our equations for when we only have one inversion or one phase change, one wave inversion. And then we're going to write out our given. So we have lambda. And for the smallest film, we'll say that M is 0 because M can start from 0. We'll have 1/2 wavelength is the smallest film that we can do for constructive interference of the red light. And then we have the index of refraction of the film in the diagram. So we're going to substitute, oh, actually, we're going to rearrange for T because that's what we're solving for. And then we're going to substitute in those givens. Index of refraction is unitless. And then our thickness is 1.1 times 10 to the minus 7 meters when you round to the number of the correct number of sig figs. So I guess the first thing to do in these problems is to draw as neat of a diagram as possible. I will expect you to use a ruler here, and you don't have to draw the wave squiggle on it, just use a ruler so it's nice and neat. And then you're going to question how many inversions exist so that you're directing yourself to the right equation. And then you're going to pick destructive or constructive. You're going to check out your givens, think about what you're solving for, select an M value or multiple M values or N values, if it's depending on if it's one inversion or two. I just want to actually go back to point out there might be a confusion because you see two N variables, but the one in the numerator is that whole number integer that is giving you the first thickness, where let's say red light will be constructive, and then the second thickness that will work for red light, and then the third. So the top number and the bottom number are both unitless, but they stand for very different things. I don't know why we couldn't have a different letter there, but it is what it is. At least there's a subscript to go with it. Any index of refraction always has a subscript to say the index of refraction of what material. So I don't know if that helps. Okay, so a classic example of the thin film interference, a very expensive example. So if anybody's into photography, you would know that camera lenses are very expensive, and among one of the reasons, there's different quality films. There's anti-glare coatings. So camera lenses are coated with a thin film. High-level coating technology uses anti-glare coatings optimized for a range of light wavelengths. Uncoated lenses produces a large amount of reflected light, both from the lens surface and from inside the lens, which reduces the amount of transmitted light and can cause image damaging flare and ghosts. And your photos will not look as good if you don't have the anti-glare coating. The color of the camera lens is based on the thickness of the coating. So you might have an example problem where you have to calculate the thickness of a camera lens coating based on the color of the light that you overall see. From the wave equation, it is important to note that when thickness of the film is expressed in terms of wavelength, we are always referring to the wavelength of the light in the film, not the air. And there's this relationship here because of the universal wave equation. And as I mentioned, there's a handful of video resources that are really helpful. Animations, explanations with examples. I find that this is a challenging topic, so I encourage you to find the resource that really resonates with you. And also, this is one of those topics where you might want to have, it should be included on a summary sheet for the chapter. Maybe you want to try and explain it to a friend and you learn something at a deeper level if you have to figure out how to explain it to somebody else, you know, and maybe they won't understand it, but you'll feel more confident explaining it and they'll know what you're going through in grade 12 physics. So for this very, it's really not as bad as I'm making it out to be when you do the examples. They are equations where you just rearrange and substitute it in, but the difficulty is in knowing which equation to use and really understanding the problems conceptually. So the practice questions, please complete all of them and submit them to Google Classroom. Also submit the exit ticket for this lesson. And I hope you have a great day. Stay safe.